Welcome back. In the previous lecture, we completed our discussion on reaction kinetics. In this lecture and the next few lectures, we'll take up a slightly different um, set of topics which are related to kinetics, but in a way different too. Okay, so we'll see what they are. So, before we start, it is good to step back and contrast what you may have seen in some of your previous uh, classes. So there is this two related topic. One is called thermodynamics. Everybody would have been introduced to thermodynamics at some level. And then there is another topic called statistical mechanics or statistical thermodynamics. What are they? So thermodynamics is description of laws, first law of thermodynamics, second law, and third law, considering matter to be a continuum. Okay, so the molecular nature are not discussed. Irrespective of the molecular nature, these laws are obeyed. So these are very powerful because we do not make any assumptions on the nature of the molecular nature of matter. So thermodynamics are very powerful set of constraints. But when you go to statistical thermodynamics or statistical mechanics, you assume certain properties of the nature of the matter, that it contains atoms. Atoms are ideal, non-ideal. They interact in this manner. Some such assumptions are made. From that, you derive some laws. Okay, so but eventually the laws which you derive from statistical mechanics rationalize the laws of thermodynamics. So in a way you give a microscopic reason for why we have first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. Especially the second law of thermodynamics involving entropy is much more clear from the basis of statistical thermodynamics. So it is typically these are introduced in the beginning, especially for engineers, and at least at an advanced level, at a graduate level, for engineers also see statistical thermodynamics. But physicists and chemists probably are introduced to statistical mechanics even in their undergraduate. So another important thing to note is that thermodynamics and statistical thermodynamics are to do with things at equilibrium. Okay, so there is some potential, either it can be free energy or entropy is maximized, extremized. Entropy is extremized, free energy is minimized. So some potential gets extremized, therefore, which defines equilibrium, and you talk about things in equilibrium. So even when things are changing, it is changing in a quasi-static manner. That means things are always very close to equilibrium. So as opposed to thermodynamics and statistical thermodynamics, when you think about reaction kinetics are things that are changing, right? You don't have chemical reactions if you are only thinking about equilibrium systems. Okay, so here in the previous set of lectures, we talked about reaction kinetics, right? There is a radioactive decay. Something is changing with time. Okay, there is some transient nature to the system. So, like we talked about thermodynamics, reaction kinetics is something at a phenomenological level. That is, there is some first order decay and so on. That is what we attempted to do. Okay, so it is typically things are measured via experiments that are documented in a mathematical manner via reaction kinetics. So, trying to interpret reaction kinetics at a molecular level is what you mean by reaction dynamics. Okay, so reaction dynamics aspires to give a mechanistic and microscopic rationalization of kinetic constants uh, obtained from reaction kinetics. So you measure data, experimental data, experimental quantities, and fit it to certain behavior, okay, some curves. From that, you can get reaction constants. Why these reactions constants are there um, from a microscopic perspective is attempted in reaction dynamics, okay? So here things are equilibrium, here things are changing. Here you, in statistical thermodynamics, you give a microscopic rationalization for things at equilibrium. In both these cases, you're not considering anything microscopic, okay, typically. So here, in both these cases, you want to give more microscopic reasons. So till the previous class, we talked about certain changes in radioactivity. We will try to get to more microscopic reasons. So here in this lecture, we have started with alpha decay. Next lectures, we will look at beta decay and so on. Okay, next set of lectures. So typically, alpha decay is observed when atomic number is greater than 82. And here I'm emphasizing again, there is an energetic driving force for decay. There is Q, there is an energy release. It's an exothermic reaction. And you can get to the nature of alpha decay, that it contains positive charges and so on, by applying magnetic field. In a magnetic field, you will have a circular path. The circular path depends upon the charge of the emitted particles. This is the magnetic field. This is the radius of the circular orbit, mass of the alpha particle, and the velocity of alpha particle. Okay, so there is a way to explore the nature of emissions by applying uh, magnetic field, electric field, and so on, and observing the behavior. This is from your basic undergraduate electricity and magnetism class. So there is something called, let's say, additional structure you see in alpha decay. Um, uh, so, so we look at these additional features in alpha decay. So here you have bismuth, radioactive nucleus is decaying into another element, and there are different energy levels for this nucleus. Okay, so this is the most stable geometry structure of the nucleus. It has the lowest energy, and these are uh, higher energy structures of the same nucleus. So what is the question we are interested in? So the first observation is that from this alpha decay, from any alpha decay, the energy that is released is distributed to the alpha particle as well as the recoiling atom. Okay, in this case, this is the recoiling atom. So between these two, the energy is being distributed, because this is from the energy conservation laws, you can write this equation, right? There are two important conservation laws, right? One is energy conservation, another is momentum conservation. Um, both these laws have to be obeyed in radioactive decay. So from energy conservation, you get this, okay? So because of the equivalence of mass and energy, we can write this relationship also. What is that you observe? The alpha particles that are emitted differ in energies. Okay, so why is that? I mean, first you get different kinds of alpha particles. So this suggests that the end product of alpha decay is different. Okay, corresponding to this, all these levels, you get different kinds of energies for the alpha particle. When you get the highest energy alpha particle, that means the decay product is lowest in energy. And if this is the energy, that is the lowest energy alpha particle, corresponds to highest energy decay product. So it is also, another feature is also important. Energetics, reaction energetics has implication to kinetics, right? We saw that the reaction energetics is different if the product is this, and so on. So because of the difference in energetics, there is a difference in kinetics also. So typically, if there is greater exothermicity, the reaction is faster. That is, this reactant decaying to this product will have the highest exothermicity. Decaying to this product will have the lowest exothermicity. Therefore, what is also observed is that typically the branching ratio is most to this product. Okay, so the branching ratio can get increasingly lesser as we go to uh, higher energy products. So this is an important feature, that is, the greater the exothermicity, faster is the kinetics. In some cases, this is not obeyed. Okay, so exothermicity may not lead to lesser reaction barriers. Why is that? Sometimes some conserved quantity, what is to be conserved might not be conserved. Okay, so there are typically two quantities. This is all related to spin angular momentum. Sometimes the spin is not conserved in some decomposition. Therefore, despite something having lower energy, might not be faster. Okay, so we won't go into this, but you should be aware of these kinds of issues as we progress. Okay, so it is this is a very general statement, but sometimes it's not obeyed because of certain rules connected with spin conservation. All these things, if you want to understand this to a greater extent, you should take a class on chemical kinetics and chemical dynamics, especially from a chemistry department. Okay, so these would be more deeply addressed in a typical class on chemical dynamics. Okay, there is another jargon which we want to clarify. So when there is a spectra, what is a spectra? We are interested in this lecture. We are interested in the spectra, the energy spectra of alpha particles. Before we get into that, we'll clarify the difference between a continuous spectra and a discrete spectra. And we will also describe what is the meaning of line width. So we'll start with differentiating continuous and discrete spectrum. One of the best example of a continuous spectrum is the spectrum of a black body, right? So here on the y-axis we have radiance. Okay, it's a measure of power output per unit solid angle and so on. Let's not. This is just take it as a measure of power output. Okay, so you have a black body at different temperatures. So this is the Wien's displacement law. So as the temperature increases, the peak is at a lower and lower wavelength. But that's all that is not too important. But what is important is that you have a continuous spectra. That is, at all wavelength, you have uh, some radiation. Okay, this is a very good example of a continuous spectra. We won't go into the microscopic reasons why that is so, um, uh, but this is a good example of a continuous spectra. As opposed to that, when you look at the spectra from an alpha decay, here or a discrete spectra, this is an example of a discrete spectra. This is an example of a continuous spectra. So in a discrete spectra, uh, there are peaks at some specific wavelength. Okay, and almost there might not be much intensity in between these wavelengths. Okay, so this is an example of a discrete spectra. This is an example of a continuous spectra. Okay, there is a monotonous increase, there is a peak, and then there is a monotonous decrease. As opposed to that, in discrete spectra, at certain specific wavelength, there is a large intensity, and then there is no continuous change here. Okay, in addition to this, there is also a line width, right? So there are reasons for line width. Okay, so we won't go into why there is a line width. Okay, so so you might have heard something called uh, Do Doppler broadening. Okay, in your previous classes. So there is also an example of width. Okay, what do you mean by line width? Okay, so typically you may expect this to be very sharp. Okay, there is no spread. Okay, you may have just lines wherein there is an intensity increase, and there is no intensity, there will be a line, there is a particular wavelength where there's a lot of intensity and the intensity goes down. But typically, instead of having a line, there is a width, okay? There is a spreading, okay? There is a, around this line, around a particular line, there is a spread, okay? Again, there are a lot of interesting microscopic reasons why there is a line width. The nature of line width also has a lot of information. We won't go into these kind of information. All we want to specify here is the difference between a continuous spectra, discrete spectra, and there is a line width associated with certain emissions. So this is an alpha spectrum. Okay, so here um, okay, this is how is this measured? There is something called a multi-channel analyzer. At different channels, the alpha particle of different energy is measured. Okay, so and y-axis corresponds to intensity. Okay, so x-axis corresponds to different energy. Y-axis corresponds to intensity. So what do you see? In alpha energy spectrum is a discrete spectrum. Okay, so you would, why is this going to be important? Okay, this is going to be important, especially when contrasted with the beta decay. Beta decay is a continuous spectrum that led to the discovery of neutrino. But as in contrast to beta decay, this is a discrete spectrum. Only in certain energy levels you have intensity, um, and there's also a line width. Okay, all this is associated with the conservation, energy conservation we wrote, right? Q is equal to E alpha plus E energy of the recoiling product, the heavier product. Okay. Okay, so the energy released is distributed into the alpha particle and the product of the alpha decay. Okay, so okay, and we move on to another topic. Uh, that is T half is inversely proportional to Q, right? This makes sense, right? If Q is larger, we said that radiation constant is greater. Therefore, because the radiation constant is related to T half, you will anticipate, okay, because we saw this in simpler case, right? For first order decay, we said that TF is is proportional to 1 by lambda, right? So based on that, we can make this statement. This also helps you get to lambda. This is the radiation constant, right? We saw the relationship in previous lectures between T half and lambda. So because Q is related to T half, we can write a relationship between energy of the alpha particle and energy of the radiation constant. Okay, this is a relationship that is often used. It is elaborated in this book, and there is another important topic. Okay, so even though there is an energetic driving force for an alpha decay, um, and the alpha particle that comes out of, let's say, decay of this has some finite energy. Okay, so what is it interesting is that um, despite this, okay, so there is a rate constant. Okay, whenever there is a rate constant, the rate constant is probably modulated via a reaction barrier, right? So we want to understand why there is a reaction barrier and what is the height of the reaction barrier. Okay, that's important to understand. Okay, so one way to look at this reaction barrier is you uh, throw a projectile. The projectile here is alpha particle of energy of 9 MeV. So how do you get these alpha particles? You have some elements that are alpha emitters. These are naturally alpha emitters and you direct those alpha particles to, let's say, this particular atom. Okay. So even when you have this much energy, alpha particle, you are still not able to penetrate this. That is by projecting, that is by throwing this projectile, it is not that you are able to release an alpha particle. Okay, that means that the reaction barrier is at least as high as 9 MeV. Okay, that is the reason for this is there is a Coulomb barrier. Okay, that is when there is a alpha particle which is also positively charged, and the nucleus is also positive charge. So there is a great repulsive interaction between the incoming projectile, which is a positive charge, and the nucleus. That is called a Coulomb barrier. So this is just by classical electrostatics, right? So 2 indicates the charge on incoming alpha particle. Z indicates the charge on the, let's say, on uranium atom. So you may quantify the Coulomb barrier via this formula. This is just like classical electrostatic repulsive interaction. So at R equal to, at a distance of this value, Coulomb barrier is about 9 mega electron volts. At it increases even to a greater number, MeV, because the distance decreases. Only at this distance, at a much shorter distance, wherein the Coulomb barrier peaks, strong nuclear forces kick in. Okay, that is an attractive interaction. So the Coulomb barrier keeps on increasing till the strong nuclear forces kicks in, right? So how is that such enormous activation barriers are overcome? Okay, so this is surprising because if you have very large activation barriers, the decay constants of alpha decay must be much smaller. But despite having fairly large activation barriers, you do see some reasonable kinetics. And what is the reason for that? To understand that, you have to use some concepts from quantum mechanics. This concept is called quantum tunneling, and this would be the topic of the next lecture. So we will take up quantum tunneling in alpha decay in the next lecture. Thank you.